Welcome to True Projects. In this video, we are going to explain about the project, which is a novel ideas based on Jaya Optimizer and Smote ENN for cyber attacks detection. Before getting into the execution, first let us understand what is the project about. Internet. Internet is growing at an incredible rate with over 5.3 billion users using it in the 2024. That's a massive number. As more people come online, more data is being transferred, and naturally the chances for cyber threats also increases. Here where network intrusion detection system comes into the play. They act like security. I mean, they are the security things that watch the network to catch any suspicious activity, whether it is malware, DOS attack, or something scanning for open ports. But even the best measures that have firewalls, encryptions, and also the password protection, they aren't enough on their own to protect us from everything. When it comes to detection attacks, that is detection attack methods, we have signature based methods and anomaly based methods. Signature based methods are great at catching attacks that we have already been trained, sort of like recognizing a well known criminal in a crowd. But if a new attack type pops up, the system might miss it. Coming to anomaly based detection, on the other hand, they try to spot anything unusual, which helps to detect new threats that don't have the signature. The downside is they can sometimes mistake normal behavior for a threat, leading to false alarms. So, while these methods are helpful, they are not perfect. And here, with the old methods, that is, we have the class imbalance issue. Imagine you're trying to train a system to catch cyber attacks, but most of the data that we are looking is just normal, that is, harmless activity like people browsing on the internet or checking the mails. The attacks which we are actually care about are much more rare, so the system gets used to seeing mostly the safe behavior and has trouble spotting the rare attacks. It's like teaching someone to spot a thief in a crowd of people, but you only show them normal everyday people. Here we have more normal cases than the malicious cases. And the other issue we have is the dimensionality problem. So here we do have the dimensionality problem. There are tons and details of the data like IP addresses, packet size, and more. So this makes the system slow and efficient. So when we process the data, it makes the system slow and less efficient. So if we want to catch those rare attacks faster and more accurately, we need to deal with the class imbalance in the data and the overload of the information. That's why the system can focus better on actual important information. So moving on to solve all these problems of the imbalanced data and too many features in the intrusion detection, we are using a hybrid approach. First, we deal with the class imbalance by using this Smote ENN technique. So this method helps by creating synthetic examples of a rare attack so the system has a more balanced view of both the normal and also the malicious activity. Now, once we have handled the class imbalance, the next step is to reduce the complexity of the data itself. That's where the Jaya optimization comes in. So after we have processed the data, Jaya helps to pick out the most important features, getting rid of the ones that aren't adding value. This not only makes the system faster and more efficient, but also improves the ability to focus on the right data. So in short, we balance the data and simplify the features to make the system smarter and quicker at detecting intrusions. And here we have tested our approach on two popular intrusion detection data sets that are UNSW and NSL-KDD. So here we are implementing, we are incorporating UNSW NB15 and NSL-KDD in which we have data imbalance that is issued addressed by using this SMORE TNN and important features are selected by using this Jaya optimization. And here for detecting intrusions, we have incorporated machine learning classifiers that are decision tree, random forest, bagging, decision tree, J48, and extra tree classifiers. So the results showed that the method effectively handles the class imbalance and improves the feature selection, making the system more efficient and accurate at detecting intrusions in complex systems. Further improve the performance in this project, we are incorporating voting classifier as the extension. It is an ensemble method that combines multiple models predictions to make the final decision stronger and more accurate. On top of that, we have developed front-end using Flask framework. This makes it easier for users to interact with the system and test it out. The front end includes user authentication to ensure secure access, providing a smooth and safer experience for anyone using the system. Moving on to implement this project, we have followed the steps of the flow of work. So let us understand the first step. So first, what we have done is we have imported the necessary Python libraries like pandas, numpy, scikit-learn, and others to handle data, machine learning models, and also the visualization. Then we load two data sets that are NSL KDD dataset and also UNSW NB15. And we understand the structure, features, and types of the network intrusions. Then we clean the data by removing any duplicate entries and also handle missing or irrelevant information to ensure the dataset is ready for analysis. Then we visualize the dataset using graphs and plots to better understand trends, distributions, and also the correlations between the features and labels. Then we convert categorical data into numerical format using label encoding to make it compatible with the machine learning algorithms. Then we have used Jaya optimization algorithm to select the most important features, reducing dimensionality and also improving the model performance. And we address the class imbalance issue using Smote ENN technique, which oversamples minority class instances and also cleans the noise from the data set. Then we split the data into training and validation sets, ensuring that the model can be trained on one portion and tested on the other to evaluate performance. And we choose several machine learning models to build using the training data set. Then in the next step, we train the models on the training set, allowing them to learn from the data and tune their parameters for better performance. And we evaluate them using accuracy, precision, recall, and F1 score, and we compare them using the graphs. After that, we have developed front-end using Flask framework. So we built a user interface using Flask, enabling users to interact with the system, including features like registration and login, supported by an SQLite database for stronger user data, storing the user data. Moving on, in the front end, users will be able to give the input feature values related to attacks, and that will be pre-processed at the backend and it will be fed with the train model. Finally, train model will be giving us the prediction in the front end of the project. Coming to algorithms used, these are the algorithms used in the project to detect the intrusion attacks. So here we have used decision tree random forest, bagging with decision tree J48, extra tree, and also the extension model voting classifier. So the extension voting classifier was performing well, so we have used it for the deployment in the front end. Moving on to the requirements, to implement this project, we need basic hardware and software requirements. Coming to hardware, we need operating system of Windows, processor of 5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Coming to software requirements, we need application of Anaconda, primary language of Python, front-end framework of Flask, back-end framework of Jupyter Notebook, database of SQLite 3, and front-end technologies are HTML, CSS, JavaScript, and Bootstrap 4. Now let's execute the project. To execute, we need to open the code folder which contains source code files. So let us open the folder. Here, these are the code folder. This is the code folder. These are the source code files in the code folder of the project. In this NSL KDD folder, so here we have dataset related attributes. So this is the dataset used in the project. And this is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap files. And here we have templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. And here in this UNSW folder, we have the UNS-NBW dataset used in the project. And here we have app.py file. This .py file contains the information related to front-end logic of the project. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in HTML templates. And here we have model files that contain the algorithm information and that will be loaded into the project code during runtime of the project. And here we have two notebook files. So here we have two Jupyter notebook files that contain a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for the data science. And here we have signup.db file. This file is a database file which is used to store the user information. And here we have the NSL and UNSW process datasets. So let's open them. So this is the NSL dataset, that is after addressing the class imbalance and selecting the important features. Let's close this. Similarly, we have also UNSW process dataset. And here in the sample file, we have the test cases that will be used in the front end to detect the attacks. Now let's execute. To execute, we need to copy the path of the code folder from the address bar of the file explorer. So I'm copying the path. Now open the Anaconda prompt. Here, using the command cd followed by the space, paste the copied path and now click on enter. This will change current directory to the code folder's path. Now we have to compile the app.py file. So give the command python space app.py and now click on enter. So this command will execute Python script and perform a runtime check for any syntax errors or logical issues. And after running the app.py file, Flask framework will host the application locally at the default address, which is the local host and the port unless configured differently. So this is the local host and this is the port. Now we have to copy this local link provided by the Flask framework and paste it in any web browser. I'm copying the link. I prefer Google Chrome, so I will paste it in that. Paste the link here, click on enter. This is the web page of the project, which is displayed in the browser. Now we have to sign up. Click on sign up and enter all the registration details if you are registering newly. I have already registered, so I will directly sign in. Give your username and the password. Click on login. We have logged in successfully and we are redirected to prediction page of the project. So now let's do the prediction, that is attack prediction for both the datasets, that is NSLKDD and UNSW NP15. First, we will do prediction using NSLKDD. So click on that. Here you can see parameters, right? These are the inputs need to be given for the attack prediction. Let us understand them first. First, we have is source bytes. These are the number of bytes sent from the source, that may be attacker or the legitimate user, to the destination during session. Next, we have is destination bytes. These are the number of bytes sent from the destination, that is server or the target system, back to the source during a session. Coming to LAN, it is a flag indicating if the source and destination IP addresses are the same, which is often used in LAN attacks, where the attacker tries to send packets to themselves to exploit certain vulnerabilities. Next, we have is wrong fragment. It refers to the packets that are improperly fragmented and may indicate attempts to bypass detection or intrusion. Coming to urgent, it indicates whether the packet has urgent flag set, which might be used in certain type of attacks. Then we have is SU attempted. It indicates the number of times a super user, that is the root login, was attempted, which could signal a brute force attack attempt. Coming to numroot, it is the number of times the system's root account was accessed or attempted to be accessed. Coming to num file creation, it is the number of files created by the user or the system, potentially highlighting abnormal behavior such as malicious process creating unexpected files. Then we have num outbound CMDs. It is a number of commands issued by the source system to external servers, which could indicate attempts to compromise external systems or exfiltrate the data. Then we have is host login. It indicates if the login was successful on the host, potentially identifying unauthorized access attempts. Coming to count, it refers to the number of connections from the source IP to the destination IP during a particular time period. Then we have SRV count. It is the number of different services accessed by the source IP, which may indicate abnormal access patterns or attempts to exploit multiple services. Coming to error rate, it is the rate of server errors in a session, which could point out to potential network intrusions or misconfigurations. Coming to SV error rate, it is the rate of the server-side errors specifically during a session, potentially highlighting issues with server handling or attack attempts. Coming to SRV error rate, it is the rate of the remote errors, which may indicate abnormal communication failures or intrusion attempts. Then we have is same SRV rate. It is the rate at which the source accesses the same service, possibly indicating repetitive access to one service, which could be a sign of probing or exploitation attempts. Then we have is SRV different host rate. It is the rate of the connections to different hosts from the same service, potentially indicating an attacker's attempt to scan multiple systems. Then we have is destination host count. It is the number of distinct destination hosts the source interacts with, which may suggest scanning or probing activity. Coming to destination host SRV count, it is the number of different services accessed by the destination host, indicating the complexity or scale of the attack or unusual behavior. Then we have is different destination host, different SRV rate. It is the rate at which a destination host interacts with the different services, which could indicate an attempt to find vulnerabilities across services. Coming to destination host, same SRC port rate. It is the rate at which destination host receives the connections from the same source port, which could indicate a more targeted attack or repetitive scanning behavior. The last one we have is destination host error rate. It is the rate of remote errors encountered at destination host, which may highlight issues due to malicious traffic or attacks. So this is about the parameters. Now let's enter them. For that, we have to open the sample file. Let's open that. Open the sample file. Here we have test cases for the two data sets. And here we have different types of attacks. Let's filter them out. So total we have 5 different types of attacks. First, let's check with the class 0. And here, first we have source bytes. So the source bytes are 0. Destination bytes are 0. Land is 0. Wrong fragment is 0. Urgent is also 0. SU attempts is 0. Num root is 0. Num file creations are 0. Num outbound are 0. In-host login is also 0. And then we have count. Count is 102. SRV count is 2. Server rate is 1. Server rate is 1. And then we have server error rate is 1. Just a minute. So here we have given count as 1 or 2, and then server count is 3, 2, sorry. Server rate is 1. Server error rate is also 1. And here we need to give same SRV is 0. So here we have to give as 0. SRV different one is 0.02. And the next one is SRV different host rate is 0. Destination host is 255. Destination host is 2. And then we have destination host port rate is 0.07. And then last value, that is here we are supposed to enter destination host. It is 0. Now click on predict. So here we got that attack is detected and it is DOS attack. So here class 0 refers to the DOS attack. Let's try entering one more set of. So here I have entered the inputs. I mean, here I have given the first test case of the class 2. I've entered all the parameters. Now let's click on predict and see what will be predicted. And here we got the prediction that attack is detected and that attack type is prov attack. Now let's try with the other case. Let's try with the third test case. So here I have entered third class labels first test case. So here I have entered all the values. Now let's click on predict. And here we got the prediction that attack is detected and it is R2L attack. It is the R2L attack. Now let's try with the last test case of NSL KDD dataset. Check the box for class 4. And here let's enter the first class label, first test case. So here I have given all the input parameters of class 4. Now let's click on predict. And here we got the prediction that attack is detected and it is U2R attack. It is the U2R attack. Now let's do the prediction for the other data set, that is the UNSW NB15, and open the test case of UNSW NB15. And here we do have parameters. We need to understand them first. So here the first parameter which we have is SPKTS. So let's understand what is this SPKTS. It is the number of packets sent from the source system to the destination during a session. A higher number can indicate more communication or potential malicious activities. Then we have is S bytes. It is the total number of bytes sent by the source to the destination. It gives an idea of how much data is being transferred during the session. And then we have is D bytes. It is the total number of bytes sent from the destination to the source, indicating the amount of data the target system is responding with. Then we have is the S load. It is a load on the source system, typically measured as the number of active connections or packets being processed. A high load might indicate suspicious activity or DDoS attack. Then coming to D load, it is the load on the destination system similar to S load but reflecting the activity and strain on the receiving system. Then we have is SIN PKT. It is the number of input packets received by the source. A higher number could indicate a scanning attack or abnormal data request. Then we have is SWIN. It is the size of the window for TCP flow control at the source. It reflects how much data the source is allowed to send before waiting for acknowledgement. Coming to STCB, it is the number of packets sent by the source by using the TCP protocol, which is important for understanding how the source communicates and nature of the traffic. Coming to DTCPB, they are the number of packets received by the destination using TCP. This helps in understanding the volume of the communication the destination system is involved in. Coming to TCP RTI, they are the round trip time that is nothing but RTT and for TCP packets, which measures the time it takes for a packet to travel from the source to the destination and back. High RTTs can indicate network issues or delays. Coming to CT, SRV, SRC, they are the number of unique connections or the sessions initiated by the source system to different servers. A high count can indicate scanning behavior. Coming to CT state, TTL, the state of the TCP connection and the time to live that is nothing but TTL value, which indicates the number of hops a packet can make before being discarded. This can help detect malicious or malformed packets. Coming to CT, DST, LTM, these are the number of connections initiated by the destination to different systems during a specific time window, which could signal unusual activity or an attempt to exploit vulnerabilities. Then we have is CT, DST, SRC, LTM. It is the number of connections between the destination and source during a given time window, giving insight into the communication patterns between the two. Coming to IS-FTP login, it indicates whether a login attempt was made using FTP protocol. Multiple failed logins attempts could signal a brute force attack. Coming to CT-SRC LTM, it is the number of connections initiated by the source in a specific time window, which can be used to track the activity levels of the source. Coming to CT, SRV, DST, it is the number of unique services accessed by the source on the destination. Multiple service access could indicate scanning or probing activity. The last one we have is ISSM IPS ports. This indicates whether the source system is using ports typically associated within certain protocols or services. For example, SMB, which is used for file sharing. This feature helps to identify unusual or potentially harmful protocol usage. So this is about parameters of UNSW dataset. Let's enter the parameters. So here also we do have multiple test cases. Let's apply filter to that. So here we have two test cases. Let's try with the class 0 and give the input. So here SPKTS value is 6. Let's enter it. The next one is SB bytes, S bytes, D bytes, S load, D load, S in packet, SWIN, STCPB, DTCPB, TCP/RTT, copy it, CTSRV, sorry, and here we have to enter CT state TTL. The next one we are supposed to enter is CT DST LTM. So we have to enter this here. The next one is CD DST SRC LTM, that is 2. The next one is FTP login, that is 0. And here we are supposed to enter some more values. So CD SRC LTM is 8, CD SRV DST is 3, ISSM IPS port is 0. Now click on predict. Input will be processed at the backend, and here we got the prediction that there is no attack detected. So here class 0 means there is no attack. Now let's try with the last case of UNSW dataset. Here Let's try the first case where SPKDS is 2, 200 are the bytes, D bytes are 0. Then we're supposed to enter the S load. So copy it. D load, it is 0. S in packet value is 0.08. The next one we are supposed to enter is S in packet. We have entered somewhere wrong. We have gone wrong. So here S load, here D bytes are 0. And here S load is 10 lakhs. So copy that, paste it here. And D load, copy the D load, paste it here. Then S in packet, paste it here. Swin value is 0. STCPB is 0. And here we have some more information related to DCPB, that is 0. TCP RTT is 0. 6 is the CTSRV. 2 is CT state. Then we have DST LTM is 2. 6. And then we are supposed to give some more values. 0, 2, 6 and 0. Click on predict. So here we got the prediction that there is attack detected. So this is how we need to execute the project. Now let's check with the graphs. Click on graph. Let's check for the NSL KDD graph. Click on that. So here first we have is a sample outcome graph. Here in the graph on x-axis we have the types of attacks that we will be detecting in the project. And here in the y-axis, we have the count of that particular attack. If you observe, normal cases are more than the attacks. Here we can understand that there is class imbalance. For this purpose, we have used a technique called Smote ENN for addressing this issue. And here we have the correlation comparison graph. This is the correlation matrix graph. This shows the correlation between individual features. And here we have algorithms which are trained on the data set that where the Smote technique is used to address the class imbalance. So these are the algorithms trained on the Smote addressed data set. And here on the x-axis we have accuracy score, and on y-axis we have all the algorithm names. And here we have precision comparison graph, recall, FN score. And here we have MCC comparison graph. And here we have the algorithms, we have the graphs for the algorithms that are trained on the normal data set where Smote technique has not been used. And this is the accuracy, this is the precision score, this is the recall, and this is FN score, and this is the MCC score. Now let's check for the other data set. And here all the models are trained on the NSL KDD dataset. Now let's check on the graphs which are trained on the UNSW dataset. So here we have sample outcome graph. Here on x-axis we have the class labels, and on y-axis we have the count of each class. And here this is the correlation matrix graph. Here these are the algorithms trained on the Smote address dataset. This is the precision, recall, FN score, and MCC score graph. And this is the all the algorithms which are trained on the normal dataset where Smote technique has not been used. And here we have classification comparison graph. Here we have precision comparison graph, recall, FN score, and MCC. So now let's click on logout. In this way, just by giving inputs required by the system, we will be getting the prediction. And here, if there is attack, it will detect which type of attack it is. If there is no attack, it will detect as there is no attack. So this is all about the project.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.